All right. Hi, everybody. Welcome to Math 60. We're going to be covering sections 3.1 and 3.2 today. This is going to be all about division. So before we get into division, recall the set of integers 0, 1, 2, 3 forever, and also the negatives, -1, -2, -3 forever. And we can do addition, multiplication, subtraction. Anytime we do that with an integer, we end up with an integer. Like 10 times 90 is still an integer, or 6 minus 40 is still an integer. But as soon as we do division, we have to expand our sets of numbers into what are called the rational numbers. So any integer plus, minus, or times another integer is always still an integer, which is one of the things that makes integers really nice to work with. But an integer divided by an integer could possibly not be an integer, right? It's possible that it's not going to be a whole number, positive or negative. So examples, 6 divided by 3 equals 2, still an integer. 35 divided by -7, -5, still an integer. Five divided by 3, that's not an integer. And I know it's not an integer because 3 times 1 equals 3, 3 times 2 equals 6, and 5 is in the middle. All right, I can't count my way to 5 using multiples of 3. I cannot count my way to 5 using multiples of 3. This is how we can tell if our fraction is an integer or not an integer. Because in general, a divided by b is an integer if a is a multiple of b. Otherwise, it is not an integer. So let's look at our examples. 6 over 3 equals 2 because 3 plus 3 equals 6. 6 is a multiple of 3. 35 over -7 equals -5 because if I take a bunch of -7s and I add them all up, and I have to be a little careful with integers as we've seen. Oops. That gets me to -35, which means if I put a minus out in front of everything, it would get me to +35. All right, but regardless, 5 of my -7s gets me to the size I'm looking for. So if you want to check to see if a fraction is an integer, you just take the bottom and you work up your multiples of your bottom. And if you land on the top, it is an integer. And if you don't land on the top, it's not an integer. Let's just do another example. I'm going to give 2 examples for all of you to do. If you're watching the video, you can pause the video. Actually, I'm going to pause the video. So if you're watching, you should also pause the video. So here's a couple examples for you to try. Is 120 divided by 8 an integer? Right? That's going to take a little bit of time if you're counting your way up, but that's all right. Is 54 divided by 7 an integer? And is 78 divided by -13 an integer? You can check those by seeing if you can, and you can guess and check. You could say, oh, I think 120 is divided by 8 because 8 times 12 is 120, and check it. Oh, no, it's not. It's not big enough. What about 8 times 14, etc.? Or you can count your way up 8s at a time. I'm going to pause the video, do this, and then by the time you unpause, I'm going to be answering these questions. All right, let's find out. 8, 16, 24, 32, 40, 48, 56, 64, 70, is 72, right? Yep, 72, 80, 88, 96, 104, 112, 120. Is 120 divided by an 8 an integer? It is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 120 over 8 is the number 15. '54 over 7, 7, 14, 21, 28, 35, 42, 49, 56. Well, one too far. Is 54 divided by 7 an integer? No. It's still a number, but it's just not an integer because 54 is not a multiple of 7. 49, and then you skip past it and get to 56. And this integer with division's a little strange. If you want to know if it's an integer, you could say, I don't care about the minus sign, right? As long as the size of the bottom divides into the size of the top. So I could do 13, 26, 39, 52, 65, 78. 1, 2, 3, 4, 5, 6. So 78 over -13 is going to be -6 because a positive divided by a negative is a negative. And that's how you check if a number is an integer. If you don't have a calculator. If you have a calculator, you can just divide them. And if there's nothing after the decimal, then it's an integer. Okay. So let's look at trying to think of a good number. Let's look at 25 over 4. Is that a number? Yes. Is it an integer? How do we know it's not an integer?
25.
Because 25 is not divisible by 4, right? 4, 8, 6, 12, 16, 20, 24, 28. I skipped it. Okay, so this is a number. This is not an integer. But about how big is it? I've done this enough. I have a little bit of intuition, right? It's a little more than 6. But one of the drawbacks of writing numbers as fractions is it can be hard to see about how big is that number. And that is often what we want to know. It's like, well, if I'm splitting 25 cookies across 4 people, about how many cookies does each person get? And you say they each get 25/4, and I'm like, well, that's not helpful. Right? Like, I don't want to do it that way. Tell me about how many whole cookies they have, and then maybe a little bit extra. So the main reason we work with decimals give us an idea of either exactly how big or about. So I'll put the about how big the number is. And this goes for our fractions. This eventually goes when we look at numbers that are represented by letters, like the number pi, right? How big is pi? Yeah, and it's not exactly that, but I know about how big it is, right? And that's useful information. That's one of the big things about decimals. The way you get a decimal most of the time is just doing the calculation in your calculator. 25 divided by 4, go ahead and give it a shot. Is it 6.25? Okay. So now I know about how many cookies everybody gets. Right, everybody gets 6 cookies, and then we say 1 for the dog or something like that, right? Even some rational numbers, for example, 54/7 that we looked at before, about how big is 54/7, that's hard to say. I could use this counting thing to help me. 1, 2, 3, 4, 5, 6, 7. So it's a little bit less than 8, right? Because 7 got me to 49, and then I went a little bit past it with 8. But again, let's just find the decimal version of this. 7 point what?
7.
Keep going.
14285714.
142857142857142. This decimal is never going to stop. But I don't need that level of precision, right? So again, about how big? Well, 54/7, if I wrote it as a decimal, it would repeat these 6 digits forever and ever and ever and ever, which is kind of cool about dividing by 7, actually. There's 14 and there's 28. I think that's kind of neat. And 57 is a little bit more than 56. And then it starts again. But anyway, the point is the decimal representation, at some point, we got to say, okay, let's cut it off. Now I don't know exactly how big it is, but I know about how big it is. And that's usually plenty of good information. Right, if I want to know if I've got let's just use cookies, 54 cookies, and I want to divide them by 7 people, I know everybody gets about 7.7 cookies. That's enough. There is, so we did this with our calculator, which is good. Your calculator is never going to show you that many decimals, by the way, right? There are other times when maybe we don't need a calculator. Or 30/10.
43.
That's 43 because we can kind of cancel the zeros, right? But the other way to look at that is to say we took 430 before the decimal point. dividing it by 10 moves the decimal point one place that way, 443.0. So dividing by 10 moves the decimal one place to the left. That's one reason why we often write fractions. Well, I mean, that's not quite what I wanted to say. That's one reason why dividing by multiples of 10 is pretty nice. And if I took 200 or 2,873 and I divide it by 100, two zeros means move the decimal place 2 points, and I get 28.73. Okay. Let's look at another example. What about 28 divided by 1,000? Well, 1, 2, 3 decimals means I move 1, 2, 3 decimals, but there's a blank space here. I just fill it with a 0. All right, so if you have to move more decimals than you have numbers in the top, you fill it in with blank spaces. And decimals like this are often written with a 0 in front of the point as well. So it's often written 0.028. Both are equally correct. All right, we can go the other way too. If I tell you that I have 0.00731 as a decimal, I want to write this as a fraction. We can count how far I have to move the decimal place. Count how far to move the decimal. 1, 2, 3, 4, 5. So I have to move it 5 places, which means the number without any decimals is divided by 1 with 5 zeros. So we have now a whole number, or maybe an integer, divided by 1 with 5 zeros. Right, in this case, 100,000. All right, anybody have questions about that? All right, let's move on. I'm just gonna start a new page. So I don't know if you've noticed, but as we move through this class, we kind of spend some time working with numbers, some time working with algebra. And we come back to numbers, and we come back to algebra. So we kind of have these parallel tracks of learning, right? Where we learn some new number skills, and then we bring that to the algebra world. So today is a number skills day. So this is section 3.2. More about division. But really, this whole section is about prime number theory. And prime number theory starts early in our mathematical lives and has generated some of the most challenging mathematical theorems to prove. There was a theorem presented in like 1898 having to do with prime numbers, and it took either over or almost 100 years to prove the theorem was true. It was a guess of like, as you go up in our numbers, how many primes will you find? That's kind of cool. So what is a prime number? Anybody? It's any whole number that can only be divided by itself and by 1. I mean, any number can be divided. So when I say by be divided, I mean evenly divided, which is not the word I like to use. I should have printed out. Let's see if I can do this. I think I can do this pretty quickly. I am just pulling up something I want to share on the screen. There's first 100 numbers. Let's figure out which of these numbers are prime. I have to warn you, you do not include the number 1 as a prime. Even though 1 is a whole number that can only be divided by itself in 1, the number 1 is not a prime. And we're going to see why in a minute. Make me a circle. Go, make sure it's not filled. Okay. What about, oops. What about the number 2? Can I divide 2 by anything other than itself? 2/3, not a whole number. 2/4, not a whole number, right? 2 could only be divided by itself and the number 1. But 2 is our very first prime. Let me, what's a lie? How do I increase the size of that? Nope. There it is. There, that's better. Okay. So 2 is a prime. Let's see, 3. Can we divide 3 by 1? Yeah, but that you can always do that. Can we divide 3 by 2 and get a whole number? Nope. So 3 is a prime. How about 4? Can we divide 4 by 2? Yep. Okay, so 4 is not a prime. How about 5? Can we divide 5 by 2? No. 5 by 3? No. 5 by 4? No. This is how you find your primes. You just kind of start working your way up and you ask yourself those questions. But there's actually a super tricky way to do it, which I really like. I'm going to show you that. It's called the sieve of Eratosthenes. I can't say the name because person was Greek. Let's count by twos. 2 is a prime. 4 can't be a prime, can it? How about 6? Can 6 be a prime? No, because it's a multiple of 2. How about 8? Can 8 be a prime? Nope. We can just mark off anything that's a multiple of 2. Are you seeing a pattern with this grid? Yeah. In fact, I could just probably take this and just do that, right? Yeah, which is kind of nice. What are all these numbers that I'm covering up? What's a characteristic of these numbers? What?
Even.
Even. These are even numbers. Exactly. Right. So we have eliminated all even numbers other than 2 as our possible primes. I'm trying to make this bigger. I'm kind of just having fun too. So, right. Now let's do 3, right? We've eliminated all the even numbers. Now let's do 3, and I'm gonna change the color just for fun, so we know we're working with a different number. 3 and 6. Oh, it's a duplicate. That's okay. Let's put it on there. What comes after 6? 9. What comes after 9? 12. And we count up by 3s. And sure, we have some repeats, but that's all right. All of these numbers I'm covering up, these are Threeven numbers, which is not a word. But why can't I make it a word? Threeven means you can divide it by 3. All right, so we cover up a bunch more. And guess what? When I was covering them up, I skipped 5. That means 5 must be prime. And then we do our 5s, and that's going to be pretty easy as well, because for 5s, it's going to be 5, 15, 25, etc., right? And also all of these ones here. But look, I skipped 7. So guess what our next prime is? 7. And guess what's our next prime after that? 11. And what's our next prime after that? 13. And then 17. And then 19. And 23. And 29. And after that, I stopped with my Threeven numbers. So I'd actually have to cover that one up again. It goes right there. 31's a prime though. Right? So you can find your primes just by knocking out all your multiples as you go along. So those are prime numbers. Here's something that's super cool. Any integer, and in particular whole numbers are what we're going to look at, but any integer is either a prime number or is built by multiplying prime numbers. All right, this is like a super cool idea from math. This is a type of math called number theory. Any integer you could think of is either itself a prime number or is built by multiplying prime numbers. Let's try a couple. 6 is 2 times 3, and 2 and 3 are both prime numbers. 16, that's 2 times 2 times 2 times 2, and 2 is a prime number. But you can use the same prime more than once. 45. Well, that's 9 times 5, but 9 itself is 3 times 3. So it's 3 times 3 times 5. When I write a number as a multiple of prime numbers, this is called the prime factorization. A factor is just a whole number that divides another number. So, and it doesn't have to be prime. 4 is a factor of 12. Because 12 divided by 4 is a whole number. Right? Because 4 divides 12. But prime factors are super useful. Your book has I like this person. I like Chris. I know Chris, he teaches here. They've got a list of how do you figure out if numbers are divisible. This is terrible. I mean, the 3 is kind of cool. The 2 is, we know even numbers are divisible by 2. There's a rule that works for 3, which isn't too bad. 4, how do you know divisible is by 4? I'm not liking this. How about just make sure it's even, and then if you divide it by 2, it's still even. Right? Because that means you can divide it by 2 times 2, divided by 4, and we'll investigate that. Don't spend much time looking at these things. Look at that disaster. Just divide it by 2 once, 2, 3 times. If you can divide it by 2, 3 times, you're dividing it by 8. So, skip it. That's page 92 and 93. How do you know if one number is divisible by another? Try it. That's what calculators are for. If you can't do it in your head, that's okay. I want you to practice being able to do it in your head. But in general, how do you know if one number is divisible by another? You try it. Is 127 divisible by 3? Let's find out. I could do it my old long division way, where first 3 doesn't go into 1, but it does go into 12, which is 4. And 4 times 3 is 12. And when you subtract them, you're left with the 7. And 3 goes into 7 2 times with the remainder of 1. Oops, not divisible. And I know I'm going fast because I don't expect you to do it this way if you don't want to. You're welcome to use your calculator. The point is, the math is knowing to ask, is 127 divisible by 3? The calculator can do the arithmetic for you, and that's totally fine. Right? No. Let's find out if a number is divisible by 8. We did that before with the 120 by counting our way up. Now we're going to do it using prime factors. Is 136 divisible by 8? Well, if it's divisible by 8, it better be divisible by 2. Because 8 is 2 times 2 times 2. And I can look at that and I know, okay, 136 is even. So yes, it definitely is divisible by 2. Let me grab my calculator and figure out what that is. 65 and another 3. I believe that's 68.
Yeah.
All right. Well, if it's divisible by 8, it better be divisible by 2 again, which is 34. And by 2 again, which is 17. Yep. 136 is divisible by 8 because the prime factorization of 8 is 2 times 2 times 2. If I divide 136 by 2 a total of 3 times, I'm dividing it by 8. Now we can start. We do grade school. Okay, now we can start talking about the greatest common factor. The greatest common factor, GCF, of two numbers. The greatest common factor always, well, actually, it's two or more. Let me write that again. Of two or more numbers is the largest number that divides all of them. A factor is a number that divides. A common factor is a number that divides all of them. And the greatest common factor is the largest number that divides all of them. So let's look at an example. Let's look at, and it's often written as GCF, and then we open a parentheses and we stick our numbers in there. 12, 21. And it means the greatest common factor of 12 and 21. Does anybody want to take a guess or already know? It is 3. Yeah, Jesse, right? Okay, sorry. I've got a lot of classes and I want to know, I want to demonstrate that I know, but I also don't want to get it wrong. So I took a risk. It is 3. And Jesse, I think you knew that because you're like, well, 3 divides 12 and 3 divides 21. Yeah, but if we don't know that, that's okay. Let's write 12 as its factored form. And in fact, let's write it in its prime factorization. 12 is 2 times 2 times 3. And if you're not sure how to get here, well, you say, okay, 12 is divisible by 2, so let me start by dividing it by 2. And when you get that, you get 6. And 6 is divisible by 2. And when you get that, you get 3. Right? So 12 is even. So let's do 12 over 2, which is 6. Right? So 12 equals 2 times 6. And 6 is even. So that means we can divide the 6 by 2 and we get 2 times 2 times 3. And 3 is a small enough prime that I recognize it as a prime number. Right? Now this was 43. Maybe I wasn't sure that's prime, but I can investigate it. So 12 is 2 times 2 times 3. And 21 is 7 times 3. And what's the largest number that's in both of these prime factorizations? 3. So 3 is the GCF, is the greatest common factor. Let's do another one. Let's do the GCF of 36 and 42. If I want to factor 36, maybe I start with the easiest factor, which is 2, right? It's even. So 36 is 2 times 18. 18 is still even. So it's 2 times 9. Oh, sorry, 2 times 2 times 9. And 9 I know is 3 times 3. So my prime factorization of 36 is 2 times 2 times 3 times 3. How about 42? 42 is even. So it must be 2 times a number. It's 2 times 21. And we were actually lucky because we already know how to factor 21. We just did it. So it must be 2 times 7 times 3. Maybe I don't always rewrite them, but I will this time just to have things lined up well. 2 times 2 times 3 times 3 is 36. And 2 times 7 times 3 is 42. Do you see any numbers in common? 3 is in common, so let me circle those. Any other numbers in common? 2. So I'm going to circle those. Aside from what I've circled, any other numbers in common? 2 and a 3 on a top and 7 on a bottom. So I've exhausted my pairs. Well, that means 2 times 3 is a factor of both of them, which is 6. My greatest common factor is 6 because the elements of 6 divide both 36 and 42. All right, next. Example. Let's find the greatest common factor of 3 different numbers. 136 and 56. Sure. So 100, I know it's even, but I also know it's 10 times 10. So you don't always have to break it down in a specific way. And I know 10 is 2 times 5. So I have a 2 times 5 times a 2 times 5. Doesn't matter that it's not in order. And we did 36. That was 2 times 2 times 3 times 3. And 56 is even, so it must be 2 times 28. 28 is also even, which is 2 times 2 times 14, which is 2 times 2 times 2 times 7. I'm teaching you it this way because it works really well when we start doing algebra and we start carrying around x's also. Because when you have a bunch of x's, you can line all the x's up. Also, because number theory is pretty cool. All right, let's look for commonalities. Any numbers shared across all 3 of them? 2. Any other numbers shared across all 3 of them? Another 2. So you can have the same number shared more than once. So what's the greatest common factor? Times 2. Right? It's 2 times 2, which is 4. Right? It's each of the circled numbers multiplied together. Let's check. It's a factor if I can divide by it. 100 times divided by 4 is 25. 36 divided by 4 is 9. And 56 divided by 4 is 14. So it is a factor. But after that, there are no other factors in common. 5 times 5 shares nothing with 3 times 3, which shares nothing with 2 times 7. So it's the largest multiplication of the primes that divide it. What is the greatest common factor of 25 and 9? Well, 25 is 5 times 5, and 9 is 3 times 3. Are there any numbers in common? Nope. So does this mean it doesn't have a greatest common factor? Well, I can always cheat and do a multiplication by 1. You can always multiply by 1. So if you have no primes in common, then the greatest common factor is 1. And lots of numbers have no primes in common. Okay, the GCF is the largest number that divides. What about the smallest number that is divided by all the others? So, for example, what is the smallest number that is divided by both 14 and 18? That's the largest number that divides both. But now we are looking for a number that is divided by, right? So numbers that are divided by 14 include 14, 28, I skipped one, 42, 56, 70, 84, 98, 112. These are numbers that are divided by 14. But I don't know if any of these are divided by 18. The numbers that are divided by 18 are 18 and 36, 54, 72, 90, 108, 126. Oh, wait a minute. There we go. 126. That's the smallest number that's divided by both 14 and 18. You see how with greatest common factor, we're getting littler? And with least common multiple, that's the words. With this other one, we're getting bigger. This is called the least common multiple of 14 and 18 is 126. LCM. And this way always works. You can count by multiples until you find a common number. But doing it using primes works too. Let's see. LCM of 14 and 18. So 14 is 2 times 7. And 18 is 2 times 3 times 3. Hold on. Yeah. I'm going to show this to you, but it's a little different way of thinking. So if you're more comfortable doing it through the counting method, I strongly support that. Okay. All right. I have some factors in common. I don't have to worry about those. Cancel them out. Because if they're in common, then they're already built into the multiple. And then I take this number and I multiply it by that number. 18 times 7 is 126. And I take 14 and I multiply it by the 3 times 3. 14 times 9, also 126. If this looks like cross multiplication from the fractions thing, it's because it's exactly the same. The main reason that math teachers teach least common multiple is to apply that to the idea of adding or subtracting fractions. And here's the honest truth. Least common multiple is not so useful. A common multiple is super useful. But it doesn't have to be the smallest one. Do you want to know a common multiple of 14 and 18? It's 14 times 18, which happens to be 252. It's not the smallest, but it's fine. It works just fine for what we need it for. The least common multiple of, let me see. Hold on. What did they got? 9, 5, 50. Yeah. The least common multiple of 350 and 64. I could work to find that out. Or I could just say, let me just use 360 times, or 350 times 64. Because whatever I need to use the least common multiple for, just the basic common multiple works as well. 22, 400. Equals question mark, but a common multiple is 350 times 64. And I'm going to show you what I mean by that, just as a little look ahead. If I want to add two fractions, like 2/3 plus 5/7, they have to have the same denominator. All right, so here we're coming back to our division idea from the previous section. And now we're going to add two rational numbers. They must have the same, they need the same denominator, which reminds me I have to define some words. And there's a really easy way to make sure they have the same bottom numbers, and that's just to multiply by whatever is missing. There's a 3 on the left side, it's missing the 7. So I multiply it by 7/7. What is 7 divided by 7? It's 1, so I haven't changed anything. But now I get 7 times 2, which is 14, on the top and 21 on the bottom, and 5 times 3, which is 15 on the top, and also 21 on the bottom. And now I can add these fractions. 14 plus 15 can all be divided by 21, which is 29 over 21. In order to add or subtract fractions, you need the same denominator, the same bottom of the fraction. And one of the ideas with the least common multiple is it tells you what that extra fraction has to be. But just think that's a lot of work. If I want to add 1 over 350 plus 1 over 64, well, I'm just going to multiply the first fraction by what I'm missing, which is a 64 over 64. And the second fraction by what I'm missing, which is a 350 over the 350. And that must be 64 over 22,400 plus 350 over 22,400. I didn't need the least common multiple. I just used what was missing. Okay, definitions to take with you. The top of a fraction is called the numerator. The bottom of a fraction is the denominator. All right. Anybody have questions? Stop the video.